Britt Lundgren and Gail Zasowski are back with us to teach us lots of stuff. Again, Britt is from the University of North Carolina at Asheville, and Gail Zasowski from the University of Utah. And they both know all about the Sloan Digital Sky Survey, and they're going to share with us a bunch of the resources that are available to us. So please take it away, ladies.
All right. Welcome back. Thank you all for sticking with us and staying through to the end of today's workshop. We're really glad to see such a big group on a Saturday when everyone almost certainly has plenty of Zoom fatigue. So we're going to make this interactive as we can, so that everyone feels engaged and you don't regret sticking with us through your mid-afternoon. So thank you for joining. So I'm going to do just a brief introduction for the agenda today and pass it off to Gail, and she's going to pass it back to me, and we're going to kind of go back and forth today. But what we're planning to show you this afternoon are some demos of some hands-on activities that are appropriate for really all ages. They've been used with younger students. They've been used effectively in high school and also with some undergraduates. So there's no real target age group here. It should be fun for all. So I already spent plenty of time earlier this morning talking about the work of the Education and Public Outreach Working Group within the Sloan Digital Sky Survey. And we have a diverse range of activities and curricular resources that we've been making available. What I talked about this morning were really the Sky Server and the Voyages website, which we'll actually demo in a few minutes for you if you haven't seen it before. Sky Server, those university level Python activities, which could also be done with some high schoolers who are real go-getters. That takes a little bit more overhead to give a tutorial, and it's a little harder to do at a distance. So I'll, encourage you to reach out to me personally if you do want to try that and run into any difficulty after today. But what we're really going to focus on today are these hands-on activities, some that use these aluminum plates, which are a key artifact of our survey and a kind of a rare opportunity for students to actually put their hands on part of a big astronomical project. At the end of today's workshop, we'll provide you with a link to a form where you can request some of these. And like I said earlier, we really are desperate for them to be going to educators and not to the scrap yard. So if you'd like some for your classrooms or for any kind of educational purpose, it's really easy for us to send a pack of 2, and we're currently distributing such packs of 2 free of charge if you attend one of these workshops and express an interest. Some educators decide after our workshops that they'd really like 10 because they want all the students in the class doing the activity simultaneously. If you do feel like you would use a larger number of these plates in your labs or classrooms, we're happy to accommodate that as well. So please do let us know if you would like more than the standard shipment of 2, and we can work with you. I do want to just briefly shout out that, there are other activities that we do as an education team within the Sloan survey. So we're involved in efforts to broaden participation. There's a really successful Sloan funded project that the SDSS has been engaged in for a number of years now, called the FAST program, the Faculty and Student Partnerships, which partners Sloan institutions who are, part of the survey formally with minority serving institutions, which maybe don't have the resources to buy into the collaboration. So that's been a really great program with a lot of exceptional work from students who've been doing summer internships with partnerships with faculty in the survey. And we also do collaborations with artists and musicians. So we have an artist in residence, Tim Fitzpatrick, who does really interesting installations with Sloan artifacts and tries to incorporate art and science to kind of broaden the audience of people who might be interested in the survey and astronomy broadly. So today, what we're going to do is briefly introduce what we're doing, which I've just done, and then spend the first half an hour of this hour-and-a-half workshop introducing you to the interactive portal for looking at Sloan data, what we call the Sky Server. We're not really going to engage with the spectra, but go through a scavenger hunt of the available imaging, which is always fun. After that, I'll give a little introduction to the SDSS Voyages site, which is meant to be a collection of resources for middle school and high school age students, but again, you know, could also work for some college applications. And we'll specifically highlight some of the plate-based activities that you can find on Voyages and ways of connecting these physical aluminum plates with the database that exists, and also getting students thinking about engineering concepts and data visualization, in addition to kind of the fundamentals of astronomy. After that, Gail's going to take over and do a little hands-on cosmology activity that kind of introduces to students the kinds of measurements that are done to measure clustering in the large-scale distribution of galaxies and quasars in the survey. And that also can be done really without too much digital interaction. So today's going to be mostly kind of hands-on and interactive. Before we get started, we would ask that you go to this tiny URL, and maybe Kevin could do me a favor and put that in the comments so that it's easy to click on. We just have a really short, like 5 questions to gauge, you know, if you're already using these websites, for instance. That would be helpful to know. If today is the first you've ever heard of the Sloan, that would be helpful to know as well. The second link here is just to all of the links that we're going to kind of showcase today, so that they're all in one place for you. It's useful to have that open in a browser throughout the workshop, if you could. And then afterwards, I'll throw this up later as well, but this link to the post-workshop survey will just have like 1 or 2 questions about whether or not you thought any of this was helpful, and then give you the opportunity to request plates for your classrooms. So I'll just leave this up and give everyone a minute to check those out. I should mention there are a couple questions about Python in the pre-workshop survey, but we won't be covering Python. It was just kind of to generally survey your interests. Okay, so if you're all done with that survey and happy to move on, could you do a little thumbs up in the either in real life or thank you or as an emoji? Great. Okay, good. Thank you. So it looks like we have maybe a majority. So we'll move on. Great. Thank you for doing that. To move on, I'm going to pass this off to Gail. We didn't want to assume that everyone had been to both of our talks previously, so we are going to just quickly give you a little bit more background on the SDSS.
All right, thanks, Britt. Okay, so before you start having to listen to us talk, we thought it would be fun to do a couple of test your intuition about astronomy and physics kind of scattered throughout this session, just to get your brain thinking a little bit. So I'm going to post a first poll question here. And this is something, and we have a couple of these throughout, and these are things that can be answered mathematically if you would like to do that, but we're just curious about whether people, just to get a sense of, it's kind of fun for people to think about the sizes of things. Like we'll be talking about a lot about sort of big data sets and big concepts in astronomy. And sometimes we forget how big or small things can be. And so we thought this would be kind of a fun question to start out with. How many people do we have in here? Actually, 20, okay. All right, let me take another 20 seconds. All right, 3, 2, 1. Awesome. All right, so what fraction of the sky as seen from Earth is covered by the sun? So here are the results. So the most popular response was 1/200,000, followed by 1/20,000, followed by 1/200, followed by 1/2000. And indeed, it is about 1/200,000. And that's over the whole sky as seen from Earth. If we're talking about the half of the sky seen by an observer at any given point of time, then it's 1/100,000 or so. So I remember when I first saw this question, I was really surprised because we think of the sun as being big, but the sky is also really, really big. So, but the sun's only half a degree across. So yeah, so only 1/100,000th of the sky that you're seeing during the daytime is actually obscured by this, or not obscured, but is actually spanned by the sun itself. Okay, so like Britt said, we wanted to give a short summary of what SDSS is. It's a bit of a tricky question. So if you were at the talk yesterday or at this morning, then you've heard us using it to refer to a data set, to a survey. Sometimes it's often used, like the term will be used to apply to the instrumentation, to the people, to the data releases and things. So SDSS is a collaboration of literally hundreds of scientists at dozens of institutions around the world. We have had members on every single continent except for Antarctica and Africa, which makes scheduling video conferences super fun when you're trying to span 17 different time zones. But all these people are working together to build a set of hardware, observe a whole bunch of different kinds of data. This is also one of the things that makes it a little tricky, is that we're not doing just imaging or just spectra or just black holes or just stars, but really everything in the universe at all times and all places. Writing codes to actually process the data into something that the researchers can use, making science, publishing science papers, giving talks, but then also packaging up all of the data to release to the whole rest of the astronomical community. One thing that's interesting to mention is that in contrast to a lot of large astronomical projects, SDSS does not receive a lot of federal funding, and actually received fairly little federal funding until relatively recently. So it's almost entirely funded by private foundations like the Sloan Foundation, which is where it gets its name, the Heising-Simons Foundation, a couple others. But the bulk of the money actually comes from the member institutions themselves. So institutions, universities will buy in to the survey, and that funding goes towards building the hardware and the software. And one of the advantages is that all of the people at those institutions then get early access to the data. But within a couple of years after the data are taken, it is periodically released to the entire astronomical community for analysis. Not only is it released to the astronomical community, it's also being released to the whole world. And so what we're going to talk about today is what people who are not necessarily professional astronomical researchers can do with the data. So scientifically, we're taking the kinds of data that can be used to study compositions of stars in the Milky Way. So what fraction of heavy elements in different elemental ratios and ages of stars all the way out to supermassive black holes. One of the other reasons why it's a bit of a complicated project is because it's been going for 20 years. So starting in the late 1990s, what we now call SDSS Legacy was the imaging portion of the survey. So this was using the large 5-filter camera that I showed pictures of yesterday, and Britt showed today, which took just images of a huge range of the sky. Unfortunately, it sort of deliberately ignored the parts of the sky that are covered by the Milky Way galaxy, which is what I care about. Can you go back one more, Britt? Sorry, I didn't. Oh yeah, and then it is imaging and took for supernovae, and then doing spectra for looking at how stars are moving and what they are made out of in the outer reaches of the galaxy. Sorry. Okay, and so this is done using, you can go to the next one. And so this was done using one telescope in the original case, and this is at Apache Point Observatory in New Mexico. It's a 2.5-meter telescope that was built for the survey. And this is one of the only reasons why so much data were able to be collected. Many astronomers have to propose for time. You get allocated certain nights at facilities that also have other instruments, also have other observing programs, and other priorities going on. But having a dedicated telescope that was doing nothing but observing for SDSS was really phenomenal. And so it's a large camera, and you can see here on the lower right, this is what sort of the inside of the camera looks like. The colors there are showing you the filters. So we're, each image being taken is only looking at one particular color of light, one particular wavelength of light, and there's 5 of those. When you combine those 5 different wavelengths together, you can learn a lot about the colors of objects in the sky. And then if you want a little bit more detail, then you take spectra, which is where now instead of looking in 5 wavelengths, you're looking in thousands of wavelengths. And so the original project was to look at almost a quarter of the night sky, do imaging over a huge range of it, and then select almost 1 million of those objects to look at in greater detail with spectra. And that phase kind of ended in 2008. By the time it ended, it had gotten more than a quarter of the night sky, more than 30% of the night sky. This is what we call the orange spider image, for I think pretty obvious reasons. And like Britt said in her talk this morning, the density of the brightness of the orange in these images is showing you how dense galaxies are at each point in the sky. And these are the place where we're looking here is if you're looking out of the galactic plane, looking straight northwards out of the galactic plane, or looking southwards out of the galactic plane. The Milky Way has a lot of dust and stuff that makes it hard to look too far into the galaxy itself. And you can see that the universe is not completely homogeneous. And this has been one of the things that people who study the early universe are very interested in, is what causes there to be this kind of structure, and what can that structure on these very, very large scales tell us about how the universe started and then how it's expanded since then. And then like here, so then currently this camera lives in the basement of the Smithsonian Museum, and at some point there will be a right time and reason to incorporate it into a display. But the fact that it's there already, the fact that it's there at all, I think says a lot about the legacy and the impact that this new type of way of collecting data has had on the astronomical community as a whole. Okay, so then, and as I said, all of the SDSS imaging data are publicly available. We'll go through a little bit of this in a while, but there's a couple of websites in various levels of modernity in which you can browse the images. You can also browse all of the spectra, and there's a whole bunch of content available to help walk people through the process and what you can actually learn from looking at these images.
Great. Thanks, Gail. So what we're going to ask you to do now is to actually navigate to this website. So you can find it at skyserver.sdss.org. There's a lot to take in on this website. It has a lot of different tools which are meant, some are meant to be used by professional astronomers, but many are also meant to provide easy access to the public. So you probably won't find everything on this page helpful or even necessarily really well organized, but some people use these frequently, which is why they find themselves on the front page. We're going to just invite you to use the navigate tool, which can be found in the upper left-hand corner of this page under data access. And if you navigate to that page, you should come to something like this, which will place you somewhere in the center of the survey image. So what we would call the footprint of our imaging of the sky. And there are, again, a lot of different tools and bells and whistles in this interactive portal. I'll just point you to a few different places where you can kind of find your reference point, the coordinate location on the sky that you're looking at. So for those of you who are familiar with the jargon of astronomy, these are coordinates of right ascension and declination, which are equivalent to latitude and longitude on the sky. So there are a number of different places where you can find the right ascension and declination that you're currently looking at. This view to your right is always going to be a zoom in of whatever it happens to be that you're centering and clicked on in the center of your field of view. But you can change the position by physically changing those right ascension and declination coordinates, or if you have a favorite object in the sky, there's a good chance that we've covered it in our survey footprint. And so you can also try typing in a proper name for an object and see if it is resolvable by the survey database. You can also kind of just scan left and right by clicking on these cardinal directions, which may not be obvious, but are buttons. And so if you click on the north, east, west, or south, you will progressively inch in one of those four directions around in the survey area. And you can zoom in or out using the kind of magnifying glass icon buttons to the left. There are a bunch of other different options for highlighting objects of interest. You can choose to put a circle around everything that has been identified as a unique object in the imaging, meaning it's just, it's brighter than the background noise. And so we think that this is a real object. You can also click on objects with spectra, and that will place a square around all of the objects that were detected in the imaging and also followed up with spectra using that multi-object spectrograph and these aluminum plates. I would also note, this is fun for students. If you find something interesting and want to not lose track of it, you can click on Add to Notes, and that will just update progressively a web-based notebook that's temporary. It will disappear if you navigate, if you close your browser and leave for the day. But for as long as you're actively working on the site, that will keep track of things that you add to notes, and you can review those at any time by clicking on the Show Notes button. And while that will disappear, if left to its own devices, you can download it into a spreadsheet and save it. So students often find that useful. As part of the spreadsheet, it will include hyperlinks that will take you to the location in the Sky server where that object is, so that you can always navigate back to it without having to manually type in your RA and DEC, which is really useful. In the link to the SDSS resources, which was shared in the chat a few minutes ago, there are a number of links to our SkyServer Scavenger Hunt activity. One of those links is a very, very long spreadsheet that just has thousands of random right ascension and declination coordinates. If your students are tasked with just exploring our data set, this can be a fun way of making sure they don't always just start exploring around the same predefined place where that the link to the navigate function will always take everyone. So that can be really helpful to make sure that your students or anyone, members of the public, are all looking at a unique part of the sky relative to everyone else who's doing the same thing at the same time. So a really fun activity that we could do right now is a scavenger hunt. And also in the SDSS resources link that has been shared with you, you can find a one-page kind of activity that is printable or could be shared as a Google Doc with students where they can keep track of the right ascension and declination of objects that they find that fit into these kind of general categories. So this is kind of like an astronomical zoo. There's a lot of stuff to see in the SDSS imaging, and very few spots in the image have been seen by a lot of people a lot of times. So oftentimes you're seeing something that's pretty underexplored, which makes this activity really fun, especially if you start somewhere kind of random. Things that you can find in the imaging, if you look around, are clusters of stars, or and those are you know, either globular clusters or open clusters. You can also find clusters of entire galaxies. Different types of galaxies, you know, anything you can imagine. The SDSS imaging, you know, generally is not going to look as sharp as a Hubble Space Telescope public release image that some of your students might be used to. They might be a little underwhelmed by the sometimes graininess of the images, but we went for scale with the SDSS. So what we've collected is the largest, I think I may have frozen. Sorry. So, you know, most of the galaxies in our survey are quite distant and they may look kind of fuzzy, but some of them are spectacular and interesting. And you may also find plenty of cases of interacting galaxies, which can look really fantastic as well. You can catch objects that are moving across that camera, which has multiple color filters in rows of CCDs. The effect of the way that our images were taken means that anything that's actually actively moving as it's being imaged will show up with its colors separated in our imaging. And so this is a nice way of identifying things that are moving, like asteroids. Typically those look kind of like stoplights because they're not moving very fast during the course of the exposure. But you can also find plenty of cases, I don't have one here, but satellite trails as well, or airplanes will often be moving so fast that they're only caught in a single color. So you can find a very bright streak of green or red or blue. And then middle schoolers love these things. We call them ghosts, but they're really just artifacts of the imaging. So oftentimes what's happening is there's a very bright object, usually a bright nearby star, that's just outside of the frame of one of the images, and its light, you know, kind of got all over the place on the CCD and spread out. And so you can get these kind of optical artifacts, which look really interesting and can be pretty distracting for some of the younger students. But like I said, you can find a large variety of galaxies. Spirals can be face on or edge on. It's all random, right? And then, you know, something that's fun and interesting as a challenge for more advanced students is to look for quasars. Okay, so quasars look like stars in the imaging, The reason being that their light is being emitted from a very small region in the center of a distant galaxy. And so effectively they show up looking like point sources in our image, when in reality they're the centers of distant galaxies, and you just can't see the extended portion of the light. Now, the only way you can really tell a quasar from a star is by looking at its spectrum. And this is a major component of the Sloan's work in terms of trying to build up larger and larger samples of these really exotic objects that we see in the very distant universe. And they're characteristically defined by these very broad emission lines, which are explained as light being emitted in a rapidly rotating accretion disk around a supermassive black hole at the center of those galaxies. And so you can see, you know, these are real images of a star in the Milky Way and a very distant quasar. Unless you had the spectrum, you wouldn't know from the color or the brightness or the shape of the image, you know, what exactly you're looking at. So, so a fun challenge for students, if you get to the point of having them actually look at the spectra in addition to the imaging, is to check for those kinds of those shapes that that identify something that otherwise looks star-like as an actual quasar. And so you can find the spectra also in the lower right-hand corner of the SkyServer window, and that's another way of kind of making this a bigger challenge. Quasars are also pretty rare, so so that can be a fun challenge for more advanced students. I might just give you all 5 minutes to explore and see if you find anything. Gail and I are on hand to answer any questions. If you see something that is weird, you can just post the link to that object in the chat, and we can try to solve some mysteries if you have any. But try it out, and also this would be a great time to let us know if you're running into any challenges using the interface.
Britt, there was one question earlier in the chat about the option for having a secure website. And I'm not sure if you saw that. It says, I realize the data are open source. However, is there another website that is HTTPS secured an option, or is this the only way to access it?
I'm
I think
not
this is the only one.
Yeah, I understand there are some concerns in some school districts about internet security. I would guess that is where that question is coming from. I don't think there's another version of this site that is more secure than what is already here. But if someone would have hacked it, they would have done it in the past 20 years, I think so. Yeah, I don't know, Gail, I don't know if you have a better answer.
No, I mean, as far as I know, this is the only platform that they've built for this.
Gail did mention earlier, there are various kind of legacy websites, kind of earlier versions of the SkyServer that you can find from earlier data releases. You can kind of see as our web aesthetic has evolved over time. But it's easy with a Google search to accidentally end up on an older version of the page, which is a little frustrating. But as long as you always go to skyserver.sdss.org, it will automatically take you to the latest, greatest version.
Yeah, and I'm going to put a link in the chat to like the actual SDSS website, the one that the astronomers use, which has a lot of technical stuff on it, but also has a lot more detail about the surveys and about the data and about everything, about the collaboration, about everything as well, which may be of use if you really get digging into the details and have some questions. It also has some links for how to email our help desk.
So I see there's a question about, is there any direction towards asteroids and near-Earth objects for SDSS and the Department of Defense? I would say, you know, the SDSS does have, there has been a limited amount of work using SDSS imaging to identify asteroids. I think Jelko has a paper on that from a while ago. I don't think we're really leading the game in that kind of detection. So our imaging wrapped up 10 years ago, and most of the imaging is not designed to catch things that are moving and to track them over periods of time. But many other surveys are leading in time domain measurements. So things like the Pan-STARRS survey, which does have some overlap with the Department of Defense, is really active in detecting near-Earth objects. Also, the LSST project at the Vera Rubin Observatory is going to be really kind of a game changer in detecting things that are moving also. So, so while you can do that with the SDSS, it wasn't really designed for it. And so there's a limited amount of, you know, asteroid work that you can extract from our data. So someone is, oh, we've got some R's and ducks rolling in. I'm gonna click on a link that someone just shared. Are there multiple stars in this field? Okay, so this one, if we click on it, right, it does look like there are multiple objects. I'm just going to click on photometric objects, which can be helpful with this, you know, discerning how many individual objects there are detected in a certain frame. So you can see that our computational pipeline, which reads in the images and processes them and looks for individual unique objects, has detected 3 different objects really in close proximity here. And if you click on them, you can actually, let me just drag this over. You can actually see that the type that's been automatically guessed by the pipeline is also shown here. So that looks to be a star. This also is a star, and this looks like a really bright star. You can't always trust the pipeline's initial determination of the object classification. Sometimes a really bright star looks very big in the image, and our pipeline sometimes interprets the very bigness of a bright star's light on the CCD as something extended, like an actually large object, like a galaxy. So sometimes those are wrong. Sometimes quasars are not properly identified. They can look like a star in that object classification. So it's not always right, but it is usually a good guess. There's also another link. Interesting. So this one looks kind of weird. I'm going to zoom in on it a little bit. I would guess it's an image reduction issue. I don't know if Gail, if you have an opinion.
That would be my guess too. I don't think this looks like an artifact, like an imaging artifact, which is still really good to know, and plays into the next question. So someone asked about the warning flag. That's that they found a warning that this object's photometry may be unreliable, and these are the kinds. They're among the many things that can happen that can lead to the photometry, which is the word that astronomers use to measure how much light is coming from an object at a given wavelength. And if you have imaging artifacts like this, like Britt said, if you have stray light, scattered light coming in from really nearby bright objects, if there were a satellite, say, streaking through your fiber, which is rare, but it's not impossible to have happened. You have all kinds of just weird things that happen throughout the optical train that can lead to known issues, which then get flagged, because often these are not things that can be recovered even in software. And so they say, well, we measure this brightness from the object, but we're going to flag it because we know that there's something weird going on here. The worrisome things are the things that are not flagged but also have artifacts, which is why we spend a lot of time paying very good people to write very good software for us, but it doesn't catch everything.
Okay, Well, this is great. This is why I love this activity so much, because you find all kinds of things that are weird that you've never seen before. I've been working on the survey forever, and you know, I've never seen this star, so I find this really fun. If you do find interesting things, right, and you have questions about them, you can contact our EPO team through that outreach@sdss.org email anytime to ask us about it. Usually we try to be responsive, yeah, but we would love to answer any questions if you see something weird. You never know, you could find another Hanni's Vorwerp, and that would be fantastic. So please do let us know if you find cool stuff.
Okay, there are a couple more questions. So one is there a plan to try to go back and re-image for comparisons? Not with the same camera. It's been taken off of the mountain, and it's been decommissioned. There are a lot of other surveys that are doing imaging of the sky in slightly different wavelengths or slightly different patches of the sky using slightly different instruments for other purposes. Sometimes to provide long time baselines to look for objects that are varying, sometimes to image things that are image patches of the sky where there hasn't been high quality data before. So not with an SDSS, but there are definitely other data sets that we can use to try to determine whether something is weird because it's an artifact or weird because something is changing in some interesting way. And I can post a link to another viewing tool for that includes some other surveys if we can maybe even do some comparisons for some of these artifacts there. And then there's another question that asks, what benefit is there for logging into SkyServer?
I'm not sure I fully understand the issue. So logging in, so the SkyServer is fully.
Do you mean maybe this, Kendra, do you mean the Sci server?
Oh, SciServer.
Because they asked you at the top. So.
I'm not logged in. I just wondered if there would be a benefit to having my students create a login code, like a way to record their information or something.
Oh, right. Okay. So I think that's a work in progress. I'm not really sure what the advantage is. I don't actually use that myself. But Jordan Raddick, who is the main developer for this, said he might be on today, but I don't think he's joined us. I'd be happy to ask about that and see. It's possible that you can save images to a SciServer file, but I can't say that I know exactly what the designed purpose is for that. That's a really good question.
Open and accessible on the web, that would be great for my online students, because it's just one more thing that they would have to do. And if there's no additional benefit, for the little things that we're doing, then that's fine.
I never use it, no. And presumably there is some good reason why it's there, but I don't use it. You don't, adding more complication to anything right now is, I think, a bad idea. Great. Okay, so why don't we move on? I do want to make sure I have time to show some of these plate activities in case you're interested in using some of those in your classes as well. So, I already talked about this previously, as did Gail. The way that we can make these maps three-dimensional in a human lifetime is to take many spectra all at the same time. And these aluminum plates have been designed in order to allow that by taking hundreds and up to 1,000 spectra all at once, so that you can simultaneously, in a single exposure pointing at the same point of the sky, obtain hundreds or even 1,000 spectra. So this has been a really effective engineering solution to this problem. And as I showed you before, these are machine drilled with really high precision in Seattle. And then they actually get transported to one of our 2 telescopes, either in Chile outside La Serena, or to Apache Point, New Mexico. And at that point, they get hand plugged and ready for a night of observing on the telescope. And I think possibly this is freezing for some reason, but I did show this earlier. So this is how these plates work. And while some get used more than once, especially if, you know, bad weather comes in when we're halfway through an exposure, or if a plate is designed to repeatedly take observations of the same part of the sky, it might get used more than once, but overwhelmingly, most of our plates are kind of single use. Oh, sorry, let me move forward. But what they do allow us to do, even in that single use, is to obtain spectroscopic information for the subset of photometric objects, which we think are high enough interest that we elect to put a fiber on them and actually get the spectrum. And that tells us all kinds of information about, you know, the identity of the object, its characteristics, its physical properties, and fundamentally how far away it is by analyzing how much redshift there is in the features that we see in the spectra. So you can think of these plates as kind of like constellations of objects in a tiny part of the sky. To give you a sense of scale, 36 full moons can fit into a single one of these plates, and yet we've had to drill thousands of them in order to tile the sky and get this census of objects in our survey footprint. So when we do have that spectroscopic information, we go from kind of a 2D constellation of this part of the sky to something that is fully three-dimensional. Some of the stars that we get spectra for are very close. They're in our own galaxy. And we also are able to capture light from quasars, which are, you know, sending light over billions of light years to reach us. So we're looking back more than half of the age of the universe in some cases when we collect light from those very distant objects. So there's a big range in a single plate. You can get a big range in distance in the objects that are collected. And like I said, this information for the objects that are targeted with holes on one of these physical plates can be found in the lower right-hand corner of that Sky Server window. And when these plates are done, when they've served their purpose, we have the option of recycling them. They're aluminum and they would be worth something, but we think that their educational value is actually worth more. And so what we're doing now is sending them to all the educators who want them to make sure that some of these, you know, really interesting artifacts, these unique pieces of the night sky, are put into places where they'll be appreciated and have some interaction with you know, students. So some of these have gone into museum installations. A student at the University of St. Andrews in Scotland made some three-dimensional installations using string and beads that connect to each of the holes of bright objects to help people visualize how redshift works in these plates. There are other installations like at the Royal Observatory in Edinburgh where they've made an interactive display where you can actually put this reader on top of one of the holes, and then it will display the spectrum on a screen. And so students can actually see the physical difference in the properties of the light from different objects on these plates. They've also been used purely for art. We have some amazingly beautiful coffee tables that people have in their offices throughout the survey. These are, if you put them in a window and backlight them, they're just beautiful. And like I mentioned before, Tim Fitzpatrick, who's our artist in residence, has done some really nice work on spectroscopy, and so, you know, he's told us that he's fallen in love with the idea of spectra and has incorporated this into some really interesting art pieces. And so if you Google him, you can find all kinds of beautiful things that he's done with pieces of our survey also. But what we really love to do with these plates is get them to teachers. And for 10 years or so, starting with a group at University of Washington in Seattle, this is the first group of teachers that ever received plates and training on how to access the data that corresponds to each of these plates. And it was so popular that we decided to expand it and have more of these workshops, not only in the US, but now we've expanded them to some of the countries where we hold our collaboration meetings, like in Mexico and Chile. And so these plates are finding permanent homes as they get adopted by educators. So we're hoping that may include some of you very soon. So, so we do have a curriculum of activities that go with these plates. So we won't ship them to you and then you'll just not even know what to do with it except make a coffee table. You can find these activities on our SDSS Voyages website under the For Educators tab. As I mentioned before, and maybe I should just put this in the box in the chat. Okay. So if you go to that website, and we do have a Spanish language version, if any of you prefer it, you just add a /es for Espanol at the end. But if you go to the English language version of the site and click on the For Educators tab, this will take you to some plate activities. And maybe I should just show you how to get there. Here we go. So if you go to the For Educators menu and go down to SDSS Plates for Education, this will take you to our website where we have all the information that you could need to actually use this plate as effective engagement in your classes. What I'm going to recommend is, if you wanted to, when you first get your plate, you'll notice that, probably hand scribbled in Sharpie, but also printed on the little tab at the top is the unique plate number that is what you'll use to identify the part of the sky that your plate corresponds to. And you can go to the SkyServer's plate browser and type in that number. It's a little complicated because different parts of our survey have different plates, but chances are if you're getting a plate right now, you're probably getting either a BOSS plate or an Apogee plate. And I happen to know that the one that's sitting behind me is one of these BOSS plates. That just means that it's mostly targeting quasars and galaxies, and it takes 1,000 fibers. It'll be pretty obvious if there aren't 1,000 holes in your plate. You're probably dealing with an Apogee plate.
Yeah, if your plate has 300 holes and 3 different colors of ink, which you can't see at all in my video, then it's an Apogee plate, and therefore looking at stars and therefore cooler. But I digress.
Wrong. Right, but all of the plates that have been observed you can find in this database, which is looking a little dated, but it works perfectly well. And you can click on any one of these individual numbers, which corresponds to an individual unique hole on the plate, and get all of the information that you want about that object. And so this can be really great for further investigations if you want students to know about the redshift of objects, or I don't know, you can do all kinds of things. Let me just navigate back. I've lost myself somewhere. Okay, so if you go back to the landing page for when you have a plate, this introduction will tell you about different types of plates and make sure you're oriented to what you have. But the activity that I want to really quickly just demo for you is found here. So if you look at this page, there's a list of different kinds of resources. This Apogee versus BOSS will really help you figure out what kind of plate you're looking at. This will tell you where to find the information about what's on your plate. And what I'm going to show you as a demo today is this SDSS Constellations using a BOSS plate, and just show you how this works. So this is a great activity that's being used across Scotland as part of the science curriculum. Every science teacher has access to check out some of these plates from their local library, and the students are using this activity in their classroom, so it's really well tested. The idea here is to get students to explore what's on the plate. So to think of all of these objects as a real slice of the sky, and to find some way of identifying which are the brightest objects, right? And so the way we do this in the Sloan, which is a really big database of information, is to use the SQL Query Language to get information and understand what we're looking at. So your students don't need to know SQL syntax. We've pre-written the query that you would need to get the information for your plate. All you have to do is copy it and paste it into this SQL search window. So you have to unlock it to just open it up and then paste this in. And once you've done that, you'll notice it won't actually work unless you change this XXXX to the number of your plate. So my plate is 7,050. And if I click check syntax just to make sure I copied it okay and everything is going to work, it looks good. And if I submit it, what you'll see is it's gone to the database, looked for the information that corresponds to this plate, and pulled back the 20 brightest objects, their location in right ascension and declination, their redshifts, their type, and also their plate coordinate in X and Y, which allows you to actually physically map out your plate and actually identify the positions of holes that correspond to objects that you're interested in. So I won't go into the gory details of the SQL query language, but there's, this will work. You could pull any information you want out of the database if you happen to be comfortable doing that with other parts of information that are included in the Sloan data. You can do that. It will work. But we've just put a really bare bones, simple search here that will allow you to get simple X and Y coordinates to find the locations of the brightest objects on your plate. So they've been ordered by brightness, and we've selected the top 20. You could change that to 50 if you wanted. You could order them by redshift instead. You could play around with hacking this query to do something more interesting if you wanted to. But fundamentally, what it's going to do is give you a way of plotting in X and Y coordinates where the brightest objects are on this plate. What you can do then, let me just kind of go back to my slides. What you can do then, I'm going to just kind of skip ahead. You can find all this information on the links I already showed, is to, you can export that information out to a CSV file, which you can open in Excel or Google Sheets, and then make a plot of those X and Y coordinates, which helps students learn how to do that if they haven't done that before. It gives them some coordinate experience if that's something that, that you want to brush up on. But then it also offers the opportunity to do some engineering in your classes as well. So it's a little bit of a trick. It takes some work to actually get your X and Y coordinates aligned on this plate. There's some good instructions on effective ways to do this, but I think it's fun just to let the students try to figure it out. They know the tabs on the top. You want to make sure your X and Y coordinates are 90 degrees with respect to each other. And the only trick is that you have to pay attention to really is the direction of positivity in X and Y, which is a little counterintuitive on these plates. But this is fun. It's fun practice with graphing. It's fun trying to work out how exactly to get that information. And once you've found the locations of those 20 brightest stars, there are a number of different things you can do, right? So Oriel Marshall, who designed this activity, likes to backlight them with Christmas lights. That's a really fun way to mark the positions. You can mark them with stickers, right? There are sticker sets that have stars of different sizes, which you could use to indicate different magnitudes and actually differentiate which of those 20 are brighter than others. You could also pull out color information from the SQL query if you wanted to. It's just the difference in 2 different magnitudes recorded by the Sloan. And so you could put in, stickers of stars with different colors as well. If you don't want to stick something directly on your plate, there are, craft stores have these little like thumbtacks in the shape of stars in different colors also. So there are a lot of different ways that you can kind of make this hands-on and make the information multi-dimensional, right? You cannot just have the position of the brightest stars marked, but also maybe higher order information, some way of encoding the amount of brightness, the relative brightness of those stars or their relative colors relative to one another. If you want to, and that's what I just said. And if you want to make it even more complicated, this would take a while to do this, but you can also make it like a chandelier and have beads kind of on strings dropping down from any of the locations of objects and have the length of the string indicated as distance. So you can get that information from the redshift. And we have these instructions on the website and a useful scale that can be used to make a scale model in Redshift. The challenge here, like I said before, is that some of these objects are very, very close. They're in our own galaxy, and others are truly cosmological in distance. So, so all of this gets students thinking about constellations and how, there's a lot going into what makes something bright. It could be, its intrinsic brightness or its distance or what it actually is as an object. All of this gets really nicely wrapped up into this kind of hands-on project. So maybe I'll just stop and see if anyone has any questions about this before before moving on to Gail's part. So someone asked, is it possible to take a schematic from the points on the plate and produce 3D printing models for sight impaired to feel the specific stars? That would be amazing. Yeah, I think that would be great. I don't know anyone who's doing that. There are groups, some astronomers in the Sloan collaboration do work with blind and visually impaired modeling. So the Astro BVI collaboration is one of these, but I don't know of anyone who's actually doing constellations. Usually people are mapping the brightness of galaxies that are spatially resolved, but that's a fantastic idea.
And there's a question about the lines drawn on the plate. Those are hand, so all of the fiber optic cables that get hand plugged into the plate, these are short cables. They're like yay big, and they're all anchored in groups around the outside of the plate. And so those regions are drawn on there to tell the pluggers which bundle of fibers should get plugged into which part of the plate. And this is done so that you don't end up with everything plugged except one hole on this side of the plate, and the only fiber that's left open is on this side of the plate and it can't quite reach. And so it's done to help the pluggers make sure that everything is kind of being distributed evenly. You don't end up with any leftovers at the end. And it is, and all of them are drawn on by hand with a Sharpie. So there's lots of art already on the plates inscribed by the pluggers themselves. Yep. That's a good question. There's lots of markings on there. Yeah.
Oh, and someone said dropping glue on the holes to mark the positions for the visually impaired. I think that's fantastic too. That's a really good idea. I have a student who's working on sonifying the spectra for some of the holes also, and she's using conductive paint so that it kind of it makes it so that if you touch or if you get your finger close enough to one of the holes, it will it'll close the circuit and produce a sound that is equivalent to the spectrum being sonified. It's not totally working yet, but we have high hopes for it. There's a lot of really interesting work that could be done in that space to make this more accessible.
And did you, sorry, Britt, I may have not paid attention, but did you mention that? So that there are a couple of activities listed on the Voyages page that describe some of these.
Oh, great. Okay. Yes. I had
It's
forgotten.
probably been a while since you looked at all of them. Here, I'll put a link to it. Yeah, everyone should probably cut and paste the chat before the meeting ends, because there's a lot of links and stuff that have gotten tossed in there that we may not remember to pull out and send around.
Thank you for reminding me.
And there's a question, is there a spectrometer for each fiber optic? No, so for BOSS, there are 2 spectrographs. So all the optical, all the visual light data are taken with 2 spectrographs that are actually mounted onto the telescope itself. And then all of the apogee data, which is actually taken in the infrared, is taken with a spectrograph that's actually in the building next door in the basement, because it's too heavy to have in the same building with the telescope itself. And all of the fibers are bundled up together and then feed into those instruments and then get spread out actually on the detector that actually records the spectra.
Great. Okay. Well, I want to make sure that we have time to show you the cosmology activity as well. So, so please reach out by email if you start looking at these activities more closely and run into any trouble. Gail, do you want me to keep showing slides, or do you want to share?
I'll go ahead and share it so I don't have to keep telling you to shift over. All right, hang on. Well, it's okay. Just you guys can see the whole mess on the desktop. All right. Let's do this. All right. Can people see that okay? Okay. Okay, so this is actually an activity that Britt actually developed, and I have used in my intro astro classes the last couple of years. And so we talked yesterday about, I mentioned yesterday, and I'll go into it a little bit here, about needing a very, very, very large data set to detect this very, very faint signal of the structure of the universe at a particular distance. And Britt's come up with a really cool activity that actually lets you kind of actually make that same measurement, but just using paper and transparencies. And we think that it's pretty easy to switch over to a digital format if you have online classes now. So clustering of galaxies. So just repeat a little bit from what we talked about yesterday, but so the cosmic microwave background, about 100,000 years after the Big Bang, it was still too hot for electrons and protons to be bound into single atoms. And so you had just a soup of protons and electrons. Electrons are really good at absorbing light. And so pretty much every time a photon tried to escape, it would interact with an electron. If you have light that can't go anywhere, then that's what we call opaque material. So the universe was opaque, but then it was still expanding, it was cooling. Eventually it got cool enough that all of the electrons, or many of the electrons, were able to rejoin with the protons to form hydrogen. Hydrogen, since it doesn't have free electrons floating around, is much more transparent to light. And so all of a sudden, in astronomical terms, the light was able to stream away. And when we look out in the night sky, if we're looking in microwaves, we actually see everywhere in the sky this glow of material, which is that surface. We call it the surface of last scattering. And it's basically the point in the universe at which all of the photons were suddenly freed up and were able to stream freely through space. And so when we look at the cosmic microwave background, and this has been measured with increasing precision over the last couple of decades, this is what we see. It looks pretty much homogeneous everywhere in the universe. And I apologize for your eyeballs if that just blasted them out. It's about 4 Kelvin, and it's very, very flat. But if we zoom in, if we change the color scale and we zoom in to now where we're looking at variations that are hundredths of a degree Kelvin, we do see some structure. We see that the background of the universe is slightly hotter in one direction than in the other direction. This isn't intrinsic to the universe. This is caused by the sun's motion, the fact that we are hurtling through space at some non-zero velocity. Okay, so we can model that, we can subtract that out. So now if we look at variations that are 1/10,000th of a degree Kelvin, we see some different structures. There's this part of the, I mean, of course, this is oriented in a particular way that aligns with the Milky Way galaxy. And so this bright, quasi-bright, this part of the sky that is 1/10,000th of a Kelvin hotter than the rest of the sky, this is from the Milky Way galaxy itself. So it's, again, not intrinsic to the background of the universe. But fine, okay, we can model that. We subtract that out. And once we're down to what, a millionth of a Kelvin, we get this kind of pattern. Okay, this is much more recent than the previous ones. It's taken with a Planck satellite within the last 5 or 10 years. So we actually know the density of the cosmic microwave background, 2.7255 Kelvin, plus or minus 6/10,000ths of a degree Kelvin. We do see these patterns in here, and these patterns are not entirely random. And this is what I was talking about a little bit yesterday. But yeah, so that will show. So you can also buy a plushie of the cosmic microwave background if one were so inclined. They're super cute. Okay, so here what we're measuring is temperature fluctuations, but in the early universe, temperature and mass, so the variations in temperature that we see here actually reflect variations in the mass density. And so you had some regions in the early universe that were more massive than others, just because the universe had these random initial fluctuations. These slightly denser regions were able to accumulate more matter. I'm going to switch to a slide that's going to be white, just so you know. So you had these small random overdensities of material. Gravity would pull matter in towards the material. There's some sort of pressure support, and so it doesn't collapse into an infinite black hole, but there's a little bit of pressure support. And whenever you have gravity pulling in, pressure pulling out, you get a quasi-equilibrium stage. We call these acoustic oscillations in analogy to the fact that these are very similar to the kind of sound waves that you get of compression and expansion in air. And so if we now turn our heads a little bit, so on the left here is the cosmic microwave background, and this is a cartoon schematic looking at different patches of sky. And these circles with the dots in the middle are representing these spherical sound waves. So you've got pressure pushing things, the pressure making these overdensities stable, gravity pulling these in. As you move to the right, this is the universe getting older, and those the same structures that result from the balance of pressure and gravity turn into the mass structures that we see today. Large galaxy clusters, the filaments of material that stretch between galaxies. So we start out with these acoustic oscillations. At the cosmic during recombination, which we call the moment when all of the electrons and protons recombined and the universe became transparent, these patterns became frozen in, dense centers, a ring around them. This is, think of it just as a standing sound wave. It's not very different than that. Once the universe became transparent, though, the photons were able to stream away, and that removed a lot of the pressure support. And so you're left with these patterns, these ring-like patterns that get kind of baked into the mass distribution of the universe. And that's really the key point here, is that due to the fact that the universe used to be super, super dense and super, super opaque, and then wasn't, you end up with this pattern of overdense blobs in the center surrounded by these rings. And that's a pattern that gets, as I said, baked into the mass structure of the universe for the rest of the universe's lifetime. And so these initial density little fluctuations, we can measure them in the cosmic microwave background as temperature fluctuations. We should also be able to measure them as mass fluctuations, mass patterns in the more recent universe. And here's a extremely cartoonized version. I think Britt showed this as well. But I think seeing this was really the first time that I really understood what people were talking about with this. So obviously this is highly exaggerated, but what this is just saying is that if you go a certain distance away from a galaxy, you have some likelihood of finding another galaxy there. You have some likelihood of finding some more mass there. And there's some level of randomness in here, but that there is some preferred distance, that if you go one of these radii away from a galaxy, you have an increased chance of finding another galaxy. And so if you're able to map what that scale is, how far away from other galaxies you find this enhancement, and okay, so if you find that, then that kind of tells you sort of what the preferred size of these overdensities are at a given age of the universe. And if you can measure what this radius is at different times in the universe's history, this is one way to track how the universe has expanded over time. How has this sort of standard distance changed over the universe's history? And so in order to do this in quote unquote real life, this was the reason that the BOSS survey exists. It's called the Baryon Acoustic Oscillation Survey. It's looking for these acoustic oscillations in the baryonic matter that makes up galaxies now. And it took Boss millions of galaxies in order to make this measurement. And so what this activity is sort of simulating that exact kind of measurement using a slightly simplified distribution of galaxies on the sky, which is, and it's actually very similar to what people do to actually measure this in a real data set. Okay, yeah, so this is just another example. So this is looking out so here's the Sloan telescope. As you look out into space, galaxies are not distributed randomly on the sky. And what we're looking for is a pattern of this primordial sound wave, where here this is just position on the sky, and then the peak here is showing the density. And so you want to say, if you're measuring some mass peak, which could be a galaxy, how far away do you have to go before you're most likely to find another galaxy? Okay, there's another example of that. And what this looks like is some measure of distance along the x-axis here. So scale, this can be megaparsecs or mega light years, or just angle on the sky, depends on whether you're measuring in 2 dimensions or in 3. And on the right hand side is some parameter, which I'll show in a second, which is just a quantification of how likely are you to find another galaxy at that distance. And so what this plot is showing is that at very small distances, you are likely to find, you are highly, if you are close to a galaxy, you are likely to find another galaxy there. And that's because galaxies live in groups, live in clusters. And if the universe didn't have this acoustic oscillation signal, then you would just see this continuous drop off. Is that as you move further and further away from a galaxy, there was no preferred distance before you found other galaxies there. But we do in fact see a small bump. There is some preferred scale in the universe that once you move further and further away, you find fewer and fewer galaxies, and then you hit some distance and suddenly you're more likely to find more mass there. And that's the signal of this ring. And so we use the technique that we use is called the 2-point correlation function. Depending on what level you're teaching classes, you may or may not have used this phrase. But it's just a way to compute on average how likely are you to find another galaxy at some distance, either angular or spatial distance, from some arbitrary point in space. Mathematically, it's just a ratio of the number of galaxies that, I'll just use galaxies. Of course, this can apply to any spatial or any distribution of objects, but this is just the ratio between the number of galaxies you measure at a fixed distance divided by the number of galaxies that you would measure if the distribution were truly random. And so if these were the same, if we were looking at if the universe was truly randomly distributed, if there was none of this underlying substructure, then these numbers on average would be the same, and you would end up with 1 - 1 for a 0 correlation coefficient, which would mean that we're now out here in the 0 part of the plot here. But if you have more real galaxies at a given distance, then you would expect, given a random distribution, then this number is greater than 1, and this is what gives you the little peak there. So we can measure this, and this works really nicely in the classroom, just using arbitrary units of radius, and then counting up how many galaxies. So given a field of galaxies, let's plunk down our measurement. Let's plunk down our measurement. Let's pick some galaxy to start with, and then let's count how many galaxies actually fall within X radial units away from that central galaxy. So in this case, this is 2. If we then take this as our central galaxy, here we get 3. If we take this as our central galaxy, we get 4. If we take this as our central galaxy, we also get 4, and so on. And so you build up a large sample of number of expected galaxies around central galaxies at that fixed radius. Okay, and then you do the same thing for random distribution, again at that same radius. So now let's take a random distribution of galaxies, and let's take the same number of central galaxies and count up how many other galaxies do we find that same distance away. There was 1 there, there's 3 here, there's none in this case. Here we have 2, here we have 2, here we have 3. And do that for a sample, we get 16. We found 20 ones in the quote unquote real universe. We found 16 in the random universe. And so this gives us a correlation function of 0.25 at this case for this radius. Okay. And so if we do this for a number of radii, then this tells us what the clustering parameter is at each radius. And lets us see, is there some preferred radius at which you are more likely to find other galaxies? So I think so you can ask students, I mean, depending on what level you're teaching at, and depending on how my students are doing, like I'll ask them either to kind of think through this logic themselves, like what would you expect if they were random? What would you expect if it were if it were in fact clustered, or just tell them. And then you plot it out as a function of radius. So here was our one measurement of our correlation at radius 1.5. And then you and rinse and repeat for different radii, and you can actually make that same plot. And I think this is really nice because you can actually then show like the real plot from a real paper that does this, and then students can sketch out their own version of it using this data, and they actually have a very similar pattern, which is really nice. So I think it's always nice to be able to make a plot that looks like what, you know, quote unquote real data look like. I can't see the chat, so if there are any questions, please just shout them out. So logistically, all this really takes, this is actually really nice. So it takes printing out a series of annually. So you print these out on transparencies, print out copies of this real galaxy field, print out copies of this random galaxy field, and then have the students just take the transparency, lay it over the sheet, shift it around using different central galaxies, and do the counting. I find I've done it with like working with groups of like 4 students. They'll split up, and then two of them will work on doing the random, 2 of them will work on doing the clustered field. One of them will count, one of them will record in each pair, and they'll combine their answers to get their clustering measurement. And then the whole class, all the different quads will come together and then combine all of their clustering measurements. And so we get a range of values at each radius, and we use that to talk about like standard deviation and mean and statistics and that kind of thing. But it's very cool. I think it's very cool. Yeah, and then after we go through the whole process, then we talk a little bit about how people do this on very large scales, which is a nice segue into computational approaches to this. You know, you have if you're trying to make more than 20 measurements, but you're trying to make several million of these comparisons, or million squared of these distance comparisons here, then we can talk about how this has to translate up into computing. This is not something that can scale by people counting one-on-one. This is then a nice segue into, or from talking about plates. So if you're measuring galaxies using these particular plates, one use of the galaxy is to actually make these kinds of measurements. So you're not learning necessarily about the galaxies themselves, but you're learning about how the distribution of the galaxies can tell us something about the universe themselves. And then I always, of course, talk about that it's people who actually make the data. I think sometimes that gets lost when we're focusing so much on the data. And then Britt has a really nice extension on here, and all of these slides we'll make sure that we can send them around, or if they're not already on Voyages, but talking about signal to noise and really using this as a nice way to emphasize like the more measurements you have of a thing and the larger your sample size is, the more robust your results are, which for my classes has been really useful to get into that a little bit. We're talking about signal to noise in general, but this provides a nice natural opportunity for there to be lots of noisy measurements that hopefully get averaged together into something that makes sense. Yeah, I think that was all. Just trying to stay in time to keep everyone from being too late. So yeah, any questions on that?
There are a couple of questions. So Ethan has asked, this is normally called the power spectrum, correct?
I can never, honestly, Britt, I may defer to you on that one. I can never remember which units go with which terminology.
So I think the power spectrum is the Fourier transform of the correlation function, I think. But usually the CMB fluctuations are measured as a power spectrum. And this is a slightly simpler measurement that can be done practically by students with very simple math.
Right, but it's referred to as the correlation function even in this not simple example. So I think, yeah, maybe there's a difference between measuring discrete counts versus a field. It is definitely related to that. I don't know.
It is related.
It is related. Sorry.
And someone else has made the point that you could easily do this online with PowerPoint, making a digital version of a transparency.
Yes.
Absolutely.
Yeah, we were actually, Britt and I were talking about this the other day when we were thinking about how to advise this for the workshop. So we, even just in PowerPoint, you can imagine one possible thing is even in PowerPoint, one student is sharing their screen in a breakout room and then just physically has a circle in PowerPoint that is moving things around and doing counting like that. Absolutely.
And I did post a link to the slides, not exactly the version that Gail has shown, but most of those same slides can be found at the link that I just shared. It's a big file. I apologize. Yeah, it's very high resolution. So be forewarned. I'm sure you can reduce the size of the file if you need to.
Any last questions for our speakers?
All right, well, thanks. Oh yeah, so well, I'll let Britt point out the evaluation at the end. I just want to say thank you so much for sticking with us. This has been a super long day for all of you, and so we're grateful. And unfortunately, we couldn't be in person because it'd be a lot more actually manhandling these plates around. Maybe next time.
Yeah, and thank you. I know Stephanie just posted a workshop evaluation form. I think that might be more general to the day. I just want to remind you, if you do want a plate, we will happily send them to you in exchange for you just rating how useful this all was. So please do let us know if we can help you out and get some of these shipped out to you. And I really appreciate you spending your afternoon with us.
We appreciate you spending your afternoon with us. And again, send your telepathic thank yous. And thank you very much. See all of you next